you can only compute the dot product of two vectors in the same Rn. And the answer to the dot product is a number. The number is given in the definition. I will show you how to compute the number, how to compute the dot product. So later on, I'm going to talk about the geometric meaning of the dot product and so on. Okay, we'll work on part 3, question 1. So maybe now let's do question 2 first. Okay. So question 1 is kind of weird. Now let's work on question 2 first. In the question, you are given a few vectors u, v, w, and l. And u and v are two vectors in R2, and w and l are two vectors in R3. Now let's recall a vector in R2 has two components. A vector in R3 has three components. Okay. Using these vectors, now the solution. To illustrate the meaning of a dot product, we'll compute some simple stuff first. So before we do question A, we compute the dot product of u and v first. To talk about the dot product for the notation, you'll have to include the dot notation. Okay. Now look at the cursor. This is the dot product. So later on, in today's class, we also talk about the cross product, in which you'll have a different notation. I'm trying to say a notation like this will not make any sense for two vectors. You have to write either a dot or a cross. The dot product is denoted by that. A cross product is denoted by this. The two things, they have two different meanings. I mean, the two operations, they have two different meanings. Now we concentrate on the dot product. Okay. I told you the dot product is a number. The definition is on the PDF. The dot product is here. Definition. Okay. The answer is a number. To get the number, all you need is to multiply the corresponding components, and then you add the products of you add the products, and then you have the dot product. Okay. Now, for instance, in this particular case, to compute u dot v, you look at u, you look at v. Okay. U has the first component of 1, v has the first component of 1. So you multiply the corresponding first components. So you have 1 times 1. And then plus the product of the second components. I mean 2 times 1. Okay. The answer is a number. You know how to compute the number. The number is 3, right? So the dot product of u and v is equal to the number 3. Okay. And likewise, you can compute the dot product of w and l. Now we compute the dot product of w and l. Okay. Very similar. Okay. It's 1 times 1, the product of the two first components, and then plus 2 times 1, the product of the two second components, and then plus 3 times 1. Okay. And then the answer again is a number. The number is 1 plus 2 and then plus 3. I think the final answer should be 6. I think it's 6, right? So correct me if you see anything wrong. Okay, and then we move on to question A. These two questions are designed to show you, to illustrate the meaning of the dot product. And then we move on to question A. Okay. The answer to A is going to be a number. In question A, we compute u dot v, the dot product of u and v, and then plus the dot product of w and l. Again, you have to include the dot notation. Okay, so the answer is 3 plus 6, so you have 9, right? A question like this is simple. It's designed to illustrate the meaning of the dot product. Okay. And then we move on to question B. Okay. In question B, u is a vector in R2, right? You see it has two components, and L is a vector in R3. I mentioned earlier we only define the dot product for the two vectors in the same Rn. So by that we mean, how do you want to answer the question? How do you answer question B, please?
Undefined.
Undefined. So you just say something like the dot product of u and l is undefined. Okay, so we have B, right? I'm trying to say to think we do not have to go over many other questions, but I will do question C. Okay. Now let's move on to C. Now remember the notation for question C. Now look at C, the mouse cursor. Okay. In question C, the meaning of the notation is we compute the sum of the two vectors. We perform a vector addition, and then we take. You want to recall the meaning of the notation? If you write two bars on two sides of the vectors, it means the length of the vector. By that we mean for question C. Actually, for all these questions, you need to know the meaning of the questions. Okay. The meaning of the notations. I mean, for question C, we are trying to compute the length of the sum of the two vectors. Okay. Now for question C, let's do that in two steps. Okay. In question C, we compute the sum of W and L first. We perform a vector addition. The answer is a vector. The answer is given by. Now, on top of the screen, you look at W, you look at L. You add the corresponding components. You have the sum of the two vectors. I believe the first component is 2. The second component is 3. The third component is coming from 3 plus 1, so you have 4, right? So that's how we compute the sum of the two vectors. The operation is called a vector addition. Okay. And then for the question, we are looking for, remember the meaning of the notation, we are looking for the length of W and plus L. Now, the sum of the two vectors has 3 components, 2, 3, and 4. You want to recall the formula we learned last time, how to compute the length of the two vectors? How to compute the length of a vector, I mean. Okay. If you know the components of the vector, then the length of the vector we just learned on Monday. Okay. If you want, you can open your course manual, unit 1. You can see the formula. But it's computed using the square root of the sum of the squares of all the components. By that I mean it's computed using the square root of 2 squared, and then plus 3 squared, and then plus 4 squared. Right. So you compute the square root of, now let's say 4, and then plus 9, and then plus 16. So anybody want to tell me the final answer? I think it's 13 plus 16. You have square root of 29, is that right? Square root of 29, I think. I think 29. Square root of 29. Okay. So that's the answer to question C. Okay. I told you earlier I'm going to skip question D, E, and F. So these guys are simple too. Okay. I'm going to skip this. I think most of these questions. Okay. Now let's go back to question 1. Okay. As long as you know the meaning of the dot product, then we can do question 1. Question 1 is kind of interesting. I'm not looking for the answers. All the vectors are vectors in Rn. If Rn is too abstract for you, you can imagine n value 3. You just imagine all the vectors are vectors in R3. Every vector has 3 components. Okay. In the question, I'm looking for if the answer to each question is a number, a real number, a scalar, a vector, or undefined. Okay. Now let's work on the questions one by one. Again, you need to know the meanings of the operations. Okay. So how about you just imagine all the vectors are vectors in R3. Okay. So tell me the stuff in the brackets. Now look at the cursor. Okay. So what is the answer for the stuff in the brackets? In the brackets, u dot v is a number, right? U dot v is a number. So does it make sense to use a number to get the dot product of a number and a vector? W is a vector in R3. U dot v is a number. So I'm trying to say, is it possible to compute? So now let's say you imagine W is a vector with 3 components, 1, 2, 1, 3, and 5. So whatever number. Okay. Is it possible to define? So now let's say a number 2 dot 1, 3, and 5. It's not a scalar multiplication, so this is undefined. Okay, so the answer to A is undefined. So let me know if you have any questions. Okay, now look at B. The same as before, U dot V is a number. Is it possible to use a number, so like 2 to, I do not write anything, okay? Is it possible to compute 2W? 2W is a scalar multiplication. This one is defined. This one is defined. I mean, the answer to B is defined. So what is the answer to question B? I mean, is the answer a scalar, a number, a vector, or undefined? The answer to a scalar multiple is a vector. Why nobody answer my question today? It's a vector, okay? So please, if you know the answer, try to write something in the chat, okay? Okay, now look at C. C is kind of interesting too, okay? U dot V is a number, 5W is a vector. Now look at the cursor. It's kind of the C, it has 2 terms, right? The first term is kind of a number, the second term is a vector. So that makes sense? Is it possible to use a number to add a vector? Tell me the answer to C, please. The answer to C? Still nobody answer my question. So can you hear me? You know that, so please. Undefined, right? Still nobody bother to. Undefined. Okay, now look at D. So what's the answer to D, please? U dot V is a number. Is it possible to use a number minus 1? What's the answer to question D? A number. Yeah, that's a number. So thank you. The answer to D is a number. Okay, now look at C. E. Now look at the E. Okay. U is a vector in R3. 3V is a vector in R3. You add the two vectors, U plus 3V, you have a vector in R3. And then you take the length. The length of a vector is a number. Is it possible to use a number to minus 1? So the answer to E is a number as well. Okay. And then the answer to F is of course a number. The meaning of the vector in F, the meaning of the answer to question F is the length. No, so this one is kind of weird. We can talk about the length of a number actually, okay? But I want to say the answer to F is undefined. U dot V is a number. We do not talk about the length of a number. We only talk about the length of a vector. Undefined. Okay. The main thing now is you need to know how to compute the dot product. As long as you are given two vectors, you know how to get the dot product. You're okay. Again, the main thing is here. Now let's say U dot V. To compute U dot V, you compute the product of the corresponding components, and then you add the products. You have the dot product, right, of the two vectors. How the dot product is going to be useful? Actually, the dot product, if you are in physics, is kind of okay. I will try to recall something in physics. The dot product. Okay. So now let's say in physics, if you have a force in that direction, you have an object in here, okay, and that's a number line. You just imagine that's a number line, okay. The force, if you drag the object using the force F in that direction by some distance, in this case, distance is a vector too, right? So now let's say the distance is d, the vector of d. For the people in physics, so what's the geometric meaning of? So what is the meaning of the dot product of f and d? So please, I know many of you guys are in physics. You know that. You learned that probably the last semester. It's work done, right? So that's the meaning of the dot product. Okay. Now we're going to give you the geometric meaning of the dot product. Now look at the PDF. I learned physics long time ago. And I think my first year of university I learned some physics, and then I never touched that afterwards. Okay. Now look at the screen. On the screen, you kind of have two formulas. The first formula shows you. So give me a little moment. I'm going to copy this onto PowerPoint so I can make some comments. Okay. On the screen, you have two formulas. One formula is kind of the geometric meaning of the dot product of two vectors. In this particular case, actually the geometric meaning is true for u and v in any dimension, in any Rn, but we concentrate on the case when n value is 2 or 3. You just imagine u and v are two vectors in R2, so temporarily, okay? So it's easier to talk about the geometric meaning. The first form is the geometric meaning of the dot product. Okay. Now let's try to understand the meaning. Okay. U and v are two vectors in R2. These two numbers are the length of u and v. Okay. And the theta is the angle between the two vectors. Now let's say if you have two vectors, so now let's say one vector is u, so the other vector is v. The two vectors will form an angle. That is the angle theta. Okay. Two vectors forms an angle. We use theta to denote the angle. And the restriction on theta is we always treat theta as an angle in between 0 and pi. Can be 0 and can be pi. So by that we mean if you see two vectors are something like this, if u is here, if v is here, so that's an angle from u to v, an angle something like this. That's an angle in between 0 and pi. Not everybody is in calculus. I'm going to use degree. For this course, it's okay to use degree measurement. Okay. I wrote pi, and pi, it means 180 degree. Okay. Again, on your calculator, you could set the calculator in degree mode. It's okay. 180 degree. For this course, it's okay. Okay. Again, we always treat an angle as an angle in between 0 degrees and 180 degrees. Okay. Even for two angles like that, we treat that thing as the angle. Okay. That's also an angle in between 0 and 180 degrees. So do you know what I mean? Okay. Now the geometric meaning of the dot product. First formula. Now look at that. Okay. The dot product, geometrically, it means the length of u times the length of v times cosine value of the angle. Cosine value of the angle. Okay. If you are not in calculus, actually calculus is a prerequisite of this course. I don't know why they're not checking this. So this semester. I'm trying to say, as long as you know how to use a calculator to get the cosine value of the angle, yeah, that's fine. Okay. The first formula, you treat the first formula as the geometric significance of the dot product. I'm not going to write that. Okay. The second formula is useful too. The two formulas are equivalent. The second form is going to be used to compute the angle between two vectors. That's the next topic. The angle between two vectors. Okay. Now we are going to use a few questions to illustrate how to compute the angle between the vectors. I think I have a few questions. Now let's work on question 3. In question 3, I'm asking you to compute the angle between two vectors. The formula we need to use is this form. Okay. In this form, if you are given two vectors, I told you how to compute the numerator. I told you how to compute the dot product of two vectors, and you also learned how to compute the length of the two vectors. Right. So it's possible to get the cosine value of the angle, and then you can use your calculator to get the angle. Okay. Okay. We'll move on. Okay. We'll do two questions like this. Now for question A. Also, a commonly used notation between the two vectors of the angle between the two vectors is something like this. I will show you the meaning of the notation. Okay. You have a formula for computing the cosine value of the angle between the two vectors. We use that notation to denote the angle between two vectors. The thing in the circle is the angle between the two vectors. Okay. Now we are trying to compute the cosine value of the angle between two vectors. Now let's copy the formula first so that you know what numbers you are looking for. Okay. On the numerator, you have the dot product of the two vectors. I'm talking about the formula in here. Now you should open your unit 1, okay, and then you can see the formulas, right? On denominator, you have the length of u, and then times the length of v. Okay. How about we just compute the numbers separately, and then we get the cosine value of the angle? Okay. Actually, it's not hard to just keep on going. So how about we just keep on going? It's okay. Okay, now u dot v, u dot v. U has two components, v has two components. If you do not know the meaning of square root, you could be in trouble actually. Okay. Now I'm trying to get the numerator, so we have square root of 3 and then times 1, right? And then plus 1 times square root of 3. You multiply the corresponding components in u and v, and then you add the products. And then on denominator, you compute the length of the two vectors. Now look at u. Now look at u, the mouse cursor. The length of the vector u, you compute the length using square root of the squares of the components. Square root of 3 squared, you have 3, right? Square 1 squared, you have 1. I mean, square root of 3 squared, you have 3. 1 squared, you have 1. I'm running this a little bit slow. Okay. I think you can follow me. You should be okay. And then the length of v, square 1 squared is 1, right? And then you have the second component squared, you have 3. Okay, now we're ready to get the answer to the cosine value of the angle between the two vectors. Okay. On the numerator, you have 2 square root of 3. You can follow me, I guess. On denominator, you have 2 times 2. Square root of 4 is 2. You have 2 times 2. I believe you have 8. Right? Now you have 4. You have 4. And then cosine value of the angle between the two vectors is actually square root of 3 over 2. Right. Cosine value of the angle is square root of 3 over 2. For the people in calculus, now you should be able to tell me the angle between the two vectors. Cosine of what angle in either degree or radian is equal to square root of 3 over 2 for the people in calculus. So the angle between the two vectors, again, you can use that notation to denote the angle between two vectors. Cosine of what angle is square root of 3 over 2? So please, in degrees or in radian. You can tell me either way. For the people who are not in calculus, now I want you to use your calculator to, you can put it either in degree mode or, yeah, that's right, pi over 6. Pi over 6 is 1/2, it's half. Anybody else? Try again. Pi over 3. Pi over 3 is right. Actually, pi over 3 is 60 degrees equivalent. Okay, 60 degrees. In this course, it's okay to use either radian or degree, it doesn't matter. Probably you are right. Sorry. Cosine. Yeah, 30 degrees is right. Sorry. I was thinking about sine. Alright, 30 degrees. That's how the dot product is useful to compute cosine by the angle between two vectors. For the people who are not in calculus, or for the people who are not too good at, who feels like you are too good at trigonometry, use your calculator. To compute square root of 3 over 2. Convert everything to decimals. And then the button you need is inverse cos. On your scientific calculator, you should have a button called inverse cos button. Okay. The button is something like this. Either inverse cos or arc cos. So do you see that button on your calculator? Convert this number to decimal, and then you compute arc cos. Use arc cos or inverse cos on your calculator, and then you should. I want you to get the angle of 30 degrees. Actually, on Friday you are going to have a question like this. Okay, now let's move on to question B. In question B, I guess you have to use a calculator to get a degree, okay, to get an angle. So very similar. Now for question B, we compute cosine value of the angle between two vectors u and v. Okay. Copy the formula first. You'll have u dot v, and then you have the length of u and the length of v. Okay. On numerator, you have the dot product of the two vectors. I think you have so now let's say 1 times -2, and then plus 2 times 1, right, and then plus 3 times -1. You multiply the corresponding components, yeah, and then you add the products. On denominator, you have the length of the two vectors. Square root of, so now let's say 1 squared, and then plus 2 squared, and then plus 3 squared. For the second vector, you have the length of v is -2 squared, right, and then plus 1 squared, and then plus -1 squared. Anybody want to tell me the numerator, please? It's -2, and then plus 2, 0, and on top, I think you have -3 on numerator. So correct me if you see anything wrong, okay? And on denominator, the length of u is 1 plus 4 and then plus 9, 14, square root of 14. Then square root of the length of v, you have square root of 4 plus 1 and then plus 1, 6. I think I got this right. Okay, now on numerator you have negative 3. On denominator, if you compute the sum of two square roots, you have square root of 96. Is that right? I think it's possible to simplify, but I'm going to show you. I think I have the answer to this in the course manual. Did I do something wrong? 84, I think. Sorry, it's 84.
Yes,
thank you.
it's
Sure, thank you.
84.
It's 84. Okay. Now it's okay to write the answer like that as inverse cos, but if you want to convert now let's practice how to use your calculator to convert this number to angle. So anybody want to tell me now use your calculator, please. Now get your calculator. I'm looking for the angle value of arc cos or inverse cos of this number, please. So get your calculator, use the arc cos function. Okay, use the arc cos button, I mean. 6 degrees. I want at least one other person. Use negative value, Harjit. Use negative value, please. I need one other person to confirm the answer. 109. Yeah, probably 109 is right. Okay. Okay. So that's how we get. Okay, cosine value of the angle is this number, and then you use our calculator to get the angle. Okay, so the angle between the two vectors u and v is 109, right? Degrees using our calculator. Okay. Sorry, I don't have a calculator handy. Actually, I rarely use calculators. Okay, thank you. So using two questions, you have seen how to compute the angle between two vectors. It's partially showing you how the dot product is useful. Okay. 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 Now one additional question, so which is super useful later in other contexts actually. Okay. For any two vectors, so now let's say u and v in R3. Now let's talk about the R3 case. Okay. Now listen to me. I'm going to give you an argument. You try to understand why. Okay. So maybe I'm going to ask you a question this way. If the two vectors are not zero vectors, none of the vector is a zero vector. If the dot product of the two vector u and v is equal to the number 0, you know the dot product is a number. If the dot product is equal to the number of 0, what can you say about the two vectors? If the dot product is equal to 0, what can you say about the two vectors?
One vector consists of all zeros.
No, Okay. So now let me try to show you what I mean in R2 case.
Perpendicular?
Perpendicular is right. Perpendicular is right. Okay. Okay. Now let me show you two particular vectors. Now let's talk about the case. So now let's say one vector is 1, 1, u is 1, 1, v is the vector. So now let's say 1, negative 1. In this case, the dot product of the two vectors is equal to the number of 0, right? If I want you to compute the cosine value of the angle between the two vectors, so later on I'm going to tell you the conclusion, but before that, if you can see the conclusion on your own, it's better. So you don't have to memorize, right? So cos value of the angle between the two vectors according to the formula is the dot product of the two vectors times the length on denominator. On denominator you have the product of the length of the two vectors. Okay. I told you the two vectors are non-zero vectors, so the length are not zeros. By that I mean the cosine value of the angle between the two vectors is equal to the number of 0. And then what can you tell me about the two vectors? Cosine of what angle is equal to 0? Cosine of 90 degrees is 0, right? In this case, I'm trying to avoid radian measurements. Which means the angle between two vectors is a right angle, is 90 degrees. Which means the two vectors are perpendicular, right? Now the bottom line, I told you why. I just told you why, okay? Now a conclusion I want you to know is probably on this slide, okay? Actually, that's a if and only if condition. Now look at the last conclusion, the theorem in here, okay? In Rn, n can be 2, can be 3. Actually, n can be anything. N can be any counting number. Two vectors are perpendicular. Orthogonal is a more formal name. You just remember orthogonal, perpendicular, the same thing. At right angle, the same thing. If and only if the dot product of the two vectors is equal to the number 0. I just told you why, right? I just told you why. If they're perpendicular, the cos value of the angle is equal to 0. So the dot product is equal to 0 using the geometric meaning. On the other hand, if the dot product is equal to 0, then the numerator in this formula is equal to 0. So the cosine value of the angle is 0. Okay. Which means two vectors are perpendicular. Harji wrote 90. I guess you'll 90 degrees is the angle formed by the two vectors. So you got the idea. The two vectors are perpendicular. Okay. Remember the conclusion. The conclusion is going to be used over and over again later in the course too. We can use the dot product to determine if two vectors are perpendicular at right angle or not. Okay. I think I have a few questions designed to illustrate if two vectors are perpendicular or not. All these questions are simple. Okay. So how about we just look at the PDF. In the question, I'm asking you to determine if the following pair of the vectors are perpendicular, orthogonal or not. Again, orthogonal, it means perpendicular. It's a more formal name for perpendicular. Okay. Now look at the first pair. These are the two vectors in R2. Easy to compute the dot product. The dot product is equal to 0. They're perpendicular, right? Again, it's if and only if condition. So by that we mean if the dot product of the two vectors is equal to 0, then you say then you can conclude the two vectors are perpendicular. if the dot product is not equal to 0, they are not perpendicular. Okay. Like the second case, they are not perpendicular. Actually, you can sketch the two vectors to C. So geometrically, you can draw the two vectors to C to convince yourself they are indeed perpendicular, right? The third case, I guess I was trying to show you the case when the two vectors are vectors in R3. In this case, the two vectors are perpendicular, right? Okay, I just told you how the dot product is useful. It's useful to compute the angle between the two vectors. Okay. One other, in particular, it's useful to determine if two vectors are perpendicular at right angle or not. Okay, so we're done the dot product. Any questions so far? Simple stuff, right? There's one other operation between two vectors, only for two vectors in R3. It's called cross product. We have learned how to compute 3x3 determinants. This one used to be chapter 1. I was trying to define the determinants. Okay, but we have learned that already. We jumped right into the definition of a cross product. For the people in physics, the torque I think is a cross product of two things. I don't remember the details, but the torque is a vector, right? Now let's imagine you're tightening a knot, so there's a torque. The torque is computed using the dot product. Sorry, I'm not teaching physics. We concentrate on how to define the cross product first, and then we talk about how to compute. Okay. Again, the cross product is only defined for two vectors in R3, not even for R2, not even for Rn, only defined for two vectors in R3. You use a notation like this, a cross, to denote the cross product of two vectors. The formula is here. The formula is on the screen. It's defined conveniently using a determinant. Remember the formula, okay? In the formula, the first row has three standard basis vectors in R3. I told you the term before, right? These three ij and k are standard basis vectors in R3. The second row consists of all the components in the first vector u. The third row consists of all the components in the second vector of v. Actually, I mentioned before, some operations in this course are not commutative. So this is another operation which is not commutative. I mean, in general, u cross v is not the same as v cross u. I think I told you before, matrix multiplication would be the only operation. Actually, that was wrong. This is one other operation which is not commutative. I will make more comments on that. Okay. But now let's concentrate on how to compute the cross product, and then we talk about the geometric meaning and everything. Okay. Calculation is not too hard. I think all of you guys have no problem to compute the determinants. Okay. Now we move on. I think I'm going to show you at least one question in real time. Okay, I will show you part for question 1. How to get the cross product of these two vectors in real time. Okay. Again, the question is to ask you to compute the cross product of two vectors. Can I introduce some notations so that it's easier for us to communicate? Okay. I'm going to use U to denote the first vector. I'm going to use V to denote the second vector. Okay. Now in the question, we are trying to compute the cross product of U and V. It's defined as follows. It's defined in terms of a 3x3 determinant. As try to memorize the formula. Okay. In the first row, you have ij and k, the standard basis vectors. In the second row, you have the three components of vector u in order. Okay. 2, 1, 3. The third row has the three components of vector v. One, 0, 2. Again, you have to include two bars to denote a determinant. Okay. Do not use round brackets or square brackets. Round brackets or square brackets are for matrices. Now we are talking about the determinant. I intentionally did not tell you earlier, but anybody want to tell me, is the answer a vector, a number, or whatever other things? The answer is a vector. The answer is a vector. You're going to see the answer is a vector. Okay. Now let me convince you. Yeah, the answer is a vector. Okay. Okay. We'll do this one slowly. I know there are many ways you could compute a determinant. You could use any row or any column, but in order to compute the cross product of two vectors, we stick on using the first row. It's always easier. Hardy, I think probably you got the answer right. Okay. I'm slower. Now follow me. Okay. Again, for a determinant, it's all possible to use any row or any column, but in order to get the cross product, we stick on using the first row for some reason. You're going to see the reason right away. Okay, now let's use the first row. Okay. You want to record the formula? If you use the first row, the formula is you include I first, right? Use the three numbers in the first row, and then at this location you're supposed to have C11. Okay. Now let me record the formula first. Okay. Probably you can recall the formula already. We use all the three numbers in the first row. Now let's use A11 to denote the number located in the first row and the first column, and then times C11, right? And then plus A12, C12, right? And then plus A13, C13. That's how we learned that, right? Using the first row. And of course, it's also possible to use the other formula. We define the 3x3 determinant in terms of many terms. So 6 terms, right? 3 terms are associated with positive sign. 3 are associated with a negative sign. You could also use that. But it's easier to use the first row to expand. Okay, in this case, A11 is I. I'm going to write I in here. Okay, so because I always want to write the numbers before a vector. Okay. That's A11. And then C11. So what's C11? So do not forget there's a sign, but C11 has a positive sign, right? So it's a 2 by 2 determinant. I think the 2 by 2 determinant is 1, 3, 0, 2. We computed many determinants. I think you know what's going on. Okay. A12 in this case is J. I'm going to write J in here. Okay. Anybody want to tell me the sign? Is the sign positive or negative? Plus, I think negative 1 to the power of 3, right? To the power of 3 is coming from 1 plus 2. Recall cofactors. Okay. And then the 2 by 2 determinant after removing the first row, the second column, the corresponding 2 by 2 determinant is 2, 3. I think I was trying to write 2, 2, 3, and 1, 2. And lastly, for the last term, the sign, there's a sign associated with the cofactor. You write k first. Okay. The sign should be positive. 1 plus 3 is 4. Negative 1 to the power of 4 is positive. I'm removing the positive sign. Okay. I'm not writing the positive sign, I mean. And then the corresponding 2 by 2 determinant is 2, 1, 1, 0. Right. Actually, if you expand using the first row, it's always the sign always has the following pattern. The signs are alternating. I think you can see why. The first term, the sign should be positive. I mean, for the cofactor, the sign is positive. And then the second term, if you use that number, the sign is negative, right? And then the last term is positive. I think Harjit just told me the answer. 2i, right? It's easy to compute the 2 by 2 determinant. Okay. 2 by 2 determinant, okay, 2i, right? The product of these two numbers minus the product of these two numbers, you look at the cursor. And then negative j, I think negative j is right. Harjit is right too. And then negative k, I think negative k is also right. Okay. Now you see the answer is a vector. Again, I want to emphasize now. Okay, the answer to a cross product is always a vector. As a vector. In physics, the torque is a vector, right? Actually, there's a better way to write the answer. So we do not use that as the final answer. So what is the final answer? If you compute 2i, you plug ij and k in. I'm going to write that a little slower, so just in case you don't see y. Okay, 2 times 1, 0, 0. Yeah, that's I, right? Minus j is 0, 1, 0, and then minus k is 0, 0, 1. Standard basis vector, right? For the final answer, I'm looking for 3 components. Write the vector as in terms of 3 components. I think that's 2, 2, 1, 2, 1, 0, right? That is the final answer. Okay. Simple enough. Okay. Again, we stick on using the first row. Okay. In order to compute the cross product, it's easier. It's much easier if we stick on using the first row. Alternatively, you could use any other formulas to compute. You're going to end up with the same thing. Okay. That's a cross product. We went over. I went over one question for you in very detail, actually, right? So the answer is 2, negative 1, negative 1. We went over this. Okay. Okay, I will give you 2 or 3 minutes to try question 2, maybe. Okay.
Sir, isn't your answer wrong then? or what you just gave us? Shouldn't it be 2, -1, -1?
Did I do anything wrong? Yeah, yeah, sorry about that. 2, -1, -1. The final answer is wrong. Why do I write 2? Why do I write 2 and 0? I don't know where that number from. 2, -1, -1. Yeah, now it looks okay. Sorry about that. Again, so please try question number 2, please. In question 2, I want you to compute the cross product of these two vectors. Okay, 1, 1, 3 and 1, 3, 2. I will give you 2 or 3 minutes. After you are done, just write the answer to question 2 in the chat, please. I like what Ben just did. When you see anything wrong, so do not ask me why. You just tell me you are wrong. So I know I'm wrong. If you ask me why, I will think why. Right? Write your answer in the chat if you are done, please. So just write the 3 components in order, please. I told you to open the unit 1. It's probably one of the questions in unit 1. Okay, it's okay to write the final answer in terms of h and k, but I still prefer to write the answer in terms of components. Okay. I think as long as you know what's going on, it's not too hard to compute, right? You know how to expand using the first row. You know how to compute 2 by 2 determinants. Again, for the purpose of getting the cross product of 2 vectors, it's okay to just remember the signs. The signs are alternative. I'm trying to say, you look at the mouse cursor. The sign associated with the first term is positive, the second term is negative, and so on. Okay, the third term is positive, right? Any questions about this? If you don't have any questions, we'll move on. Or are you still trying? I will move on now. Okay, I'm going to move on. Okay, if you know how to do question 1 and question 2, so question 3 is very similar. Okay, it's very similar. Probably do you bother to do question number 3 or? Sorry, it's not in the notes actually. It's not in the notes. So we did question 2. Okay, in question 2, if I'm using u to denote that vector, if I'm using v to denote that vector, you just told me for question 2 the cross product of u and v. the cross product of u and v is equal to a vector with 3 components, -1, 1 and 2. Sorry, -7, 1. I'm pretty sure in question 3, my intention for question 3 is ask you to reverse the order of the 2 vectors v, the cross product of v and u. You know what I mean? You look at 2 and 3, the 2 vectors are the same vectors but in reverse order, right? Anybody very quickly want to tell me the answer to question 3? I know the answer to 3, but somebody? Anybody? U cross v, please. So please try to do something. I have been trying to use these questions to motivate some other properties. If you do not try, you might miss something. Sorry. For question 3, I was talking about that question 3. I'll put it here. I'm talking about that question 3. If I use u to denote the vector 1, 1, 3, if I use v to denote the vector 1, 1, 3, 2. In question 3, I'm trying to ask you to compute the cross product of v and u, right? The notations of u and v in 2 and 3 in questions 2 and 3 are the same. So that's vector v, so that's vector u. So anybody want to tell me the answer to u cross v? Yeah, I think Hardy got it right too. Okay, u cross v has the first component 7, right? The first component 7. Can I write 7 that way? And the second component is -1. The third component is -2. Using these 2 questions, I was trying to motivate a property. Now listen to me carefully. It's not accidentally true. I told you earlier, cross product is not commutative, but there's a relation between u cross v and v cross u. In general, the following property is true. Okay, for any 2 vectors in R3, it's not commutative. But if you reverse the order of the 2 vectors v and u, they are differ by a negative sign. So by that we mean if you get what I'm trying to say, if you get the opposite of all the components, and then you have the cross product of v and u. You see what I mean, right? 2 and 3, the 2 vectors, but for the cross product, the order is different. Okay, this is another operation you have seen which is not commutative. Okay, right? something like when you're tightening a knot. I told you the torque is a vector which computed using the cross product of two things, right? You imagine if you're tightening a knot. Sorry, I don't want to talk about physics. I could say something wrong. Okay. You just remember mathematically that's a relation you need to know. My next question is designed to motivate another concept. Okay. So question 4. To motivate another property, I mean. Now look at question 4. I think Simran told me the answer already. For these two vectors, if I'm calling the first vector u, the second vector v, probably you have computed already. For these two vectors, the cross product of u and v is equal to 0 vector. I think that's the question Simran told me the answer. Okay. The answer to the cross product has 3 components. All the 3 components are zeros. And then I want you to kind of imagine the location of the 2 vectors or sketch the 2 vectors in R3. It's hard to sketch the 2 vectors in R3, but I think it's easy to see a relation between the 2 vectors. So do you want to tell me a relation between 2 vectors u and v? How to write v in terms of u? So do you see the vector v, the second vector in here? Now look at the mouse cursor. The second vector in here is -2 times u, right? A scalar multiple. I mean, v is -2 multiples of u. That's the meaning of the scalar multiple. In particular, in R3, in the space, I want you to imagine the 2 vectors are parallel, right? The 2 vectors are in either the same direction or reverse direction. We mentioned the geometric meaning of scalar multiple. In this case, we just say 2 vectors are parallel. Okay. I was trying to use that question to motivate another conclusion. If 2 vectors are parallel, then the cross product is equal to the 0 vector. In R3, we use the 0 vector to denote that. Okay. I will show you the conclusion on PDF in the course manual right now. Okay. Now the first property, the cross product is a vector. I told you that. Okay. The second property, I also mentioned that already. Okay. The fourth property, I will get to the third property soon. Now look at the fourth property number 4. Okay. 2 vectors are parallel in the same or in the reverse direction if the cross product of the 2 vectors is equal to 0 vector. I was trying to use that question to motivate the property. Okay, so just remember that. Okay, now let's go back to question number 2. Okay. We use these 3. I'm going to use u and v to denote the 2 vectors. Okay. U is for the vector 1, 1, 3. V is the vector 1, 3, 2. Okay. I want you to see some other things interesting. Okay. Anybody want to compute this? So please, anybody want to compute this? So by that we mean I want you to compute the dot product of u. U has 3 components, 1, 1, 3 and the cross product of u and v has three components: -7, 1, and 2. I'm going to motivate another property. Now I want you to compute the dot product, please. So what is the dot product of these two vectors?
0.
0 is the number 0. Is the number 0. The dot product of two vectors is equal to the number 0. It means what is the relation between the two vectors? We just mentioned earlier.
Perpendicular.
Perpendicular, right? Perpendicular. This means u is perpendicular. Can I use that notation for perpendicular? It's a standard notation in geometry. The vector u is perpendicular to the... Okay, now let me write the other way. I was trying to say u cross v, the cross product, is perpendicular to u. And likewise, very similarly, if I want you to... Can I write 0 in here? Very similarly, if I want you to compute the dot product of v and the cross product of u and v, so don't be confused. Cross product is a vector, v is a vector. It's possible to compute the dot product of two vectors, right? So in this case, you compute v has three components: 1, 3, 2. Okay, and cross product of u and v has three components: -7, 1, and 2. Anybody want to tell me this number again? I think very quickly. It's also 0, right? Which means u cross v is also perpendicular to v. So does that make sense? Now the conclusion. A conclusion I want you to know is geometrically, the cross product is perpendicular to both of the vectors u and v. I will show you the property on PDF. Okay. Now look at number 3. U cross. The property is true for any three vectors, not only for the two particular vectors u and v in the question. It's true for any three vectors. Okay. Now look at the property. U is perpendicular to u cross v. V is perpendicular to u cross v. So we have mentioned the property already. Okay. Actually, more precisely, we can talk about the cross product. Now look at number 5. Okay. When defining a vector, we need to talk about the length and the direction, right? Okay, now look at the length. The length of the cross product is defined that way. Actually, it's a property. It's not defined. The length of the cross product of u and v is computed that way. Okay, the length of u, the length of v, and times sine value of the angle. And we also need to determine the direction of u cross v. Okay, the direction of u cross v. I did not write it in the cross manual, but the direction of u cross v is determined by the right hand rule. The right hand rule. Okay. By the right hand rule. Okay. Now get your right hand. Now use your right hand, please. Use your right hand. Now we are trying to determine u cross v. Okay. So, how about we use a particular case to compute u cross v? Okay. If I I set u to be the vector I. So now let's say the vector with 3 components, 1, 0, 0, and v is the vector with 3 components. So now let's say 0, 1, 0. Now I'm trying to determine the direction of u cross v. Okay. In R3, that's x-axis, right? That's y-axis. So yeah, that's z-axis, right? The unit vector 1, 0, 0 is a vector here we mentioned before. The vector v is 0, 1, 0. That's essentially the vector j in here, right? I'm trying to say that's vector u, so that's vector v. Now we're trying to determine the cross product of u and v. Okay, now get your right hand, please. Get your right hand. Okay, the cross product is upward. Actually, the cross product is in that direction, right? You got me? Sum in the direction of u, index in the direction of v, then the middle finger will give you the direction of the cross product. That's the right hand rule.